In this example, we have another related rate problem. We have gases escaping a spherical balloon at a rate of 4 cubic centimeters per minute. How fast is the surface area shrinking when the radius is 24 centimeters? So they're talking about volume because we have a cubic measurement, and then they're talking about surface area, and they're talking about spheres. So we need our formulas associated to that. So we have sphere, right? It has a radius. We'll give it a circular feel to it, three-dimensional feel to it, right? And so let's organize what we have, what we're looking for, all that good stuff. So we are given that we have a gas escaping a spherical balloon at a rate. So we have this constant rate. So that is the change in your volume with respect to time. And that is going to be 4 centimeters, 4 cubic centimeters. However, the balloon is escaping, so it's shrinking, which means we should apply a negative rate to that. So cubic centimeters per minute. All right, negatives and positives matter, right? If something's expanding, then we want to have a positive kind of a rate to it. If something is shrinking, then we want a negative rate to it. So it says how fast, we'll talk about the way that they ask that in a minute, is the surface area shrinking when the radius is 24 centimeters. So we're going to use these formulas. So the very first thing is they give us a very particular rate or a very particular radius. So we're trying to find how the surface area is changing. So we're going to find the rate at which the surface area is changing with respect to time when our radius exactly is 24 centimeters. All right, but we're given the rate at which the volume is constantly changing. So we're going to start with a volume formula because we have a dV/dt. So we need to find a dV/dt, which means we need to take our volume formula and apply the derivative to it. And then we can sub in that value. So let's do the derivative of this with respect to time. All right. So this is very much an implicit differentiation. We're going to do the derivative of v, which is 1. Then it's going to be dV/dt. And that's the value we know. So we'll be summing that in a minute. And then if we do this one, we're going to be multiplying the 3 out. Now, pi, remember, is not a variable. R is the variable. So 3 is going to come in front, and it's going to multiply with the 4/3. But let me kind of put all this first. So we got a 4/3 pi that we're really not doing much with quite yet. We do the derivative of this, it's going to be a 3r squared dr dt because we're doing the derivative of the radius with respect to time. So I can cancel those, and we're looking at a dV/dt, which we know is -4. And then we have 4 pi, and we know the radius at a very particular moment. So we have 4 pi times 24 squared dr dt. Okay, so we're still going to get a variable out of this. So let me pause for just a second. That eventually we are trying to figure out how fast the surface area, the rate at which the surface area is changing, which means we're going to have to do the derivative of this. So we're going to get a dSA dt, right? But when we do it, we're going to get also an r, and we're going to get a dr dt. Well, that's why this formula exists. That's why we do our volume, because solving for this, we're going to get a dr dt. And then we can use it for our next derivative. Okay, so you're doing the derivative of something to be able to solve for a piece, so then you can apply it to the next piece. So right here, we're going to try and get this piece by itself. I'm not going to bother trying to multiply that out. I am just going to take this value, whatever it is, and I'm going to divide it over. Let the calculator do the work. All right, so if I plug that in, I will get a rate, the dr dt. So the rate at which the radius is changing from this volume with this rate in this particular moment in time, right? It's constantly getting smaller and smaller and smaller, but at this moment, we have a particular rate at which it's changing. So when you throw that all into the calculator, this is going to get us a negative 0.00055, bunch of values. Now I'm going to store that onto my calculator, right? Like, let's not clear anything out, because let's be as accurate as possible. So if I do that, let's just kind of show it. I get a negative 4 over 4 pi times 24 squared, right? So there's my scientific notation. So then I'm going to bump that decimal back 4 spots, which is going to give us this, but I'm going to keep the whole thing, right? I'm going to constantly use the most accurate possible answer I can, because now I need this to apply it to the next thing. So this is where we go into surface area. So our surface area formula is 4 pi r squared, and we are going to do the derivative with respect to time. So that's going to be d SA dt equals, and if we do the derivative here, that's going to make this an 8 pi r times dr dt. All right. So based on the stuff that we have a very particular radius, and we also found a rate at which the radius is changing. So we can sub all those values in, and once we plug it into a calculator, we're going to have our answer. So we're going to have an 8 pi times our radius of 24 is our moment, and then times this rate at which this is changing. And I'm going to use the whole value on the calculator to keep it as accurate as possible. And then I'll have my answer. And so if you notice, I'm going to have a negative answer, and that should be happening because if this ball is shrinking, then our surface area is going to be shrinking. So we should have a negative answer. But our final answer is going to be how fast is the surface area shrinking. So they've already brought up the word shrinking, so I don't need to tack a negative onto it. Our answer is going to be negative, but then what I would be like listing out as, well, my work's going to be negative, and then what I would list out as my answer would just be the value. So we have 8 pi times 24 times that value, and there is the rate. So that is actually a third. So apparently all this stuff, if I didn't use a calculator, would have all simplified out pretty nice. And so I get a negative 0.33 on centimeters squared per minute. So my actual answer is, this is a third. So our rate at how it's shrinking is 1/3 of a centimeter squared per minute at that moment. All right, so that's how I'm going to kind of finish my answer. So it is shrinking. I did get a negative, but then it already told me it was shrinking, so then I can just take that. And I know that 0.3 on forever is a 1/3. And that's my final answer.